In this video, I will give the proofs for these differentiation rules. First, we have dk over dx equals to 0, where k is a constant. If we draw the graph y equals to k, then the graph will be a line parallel to the x-axis. The derivative is the slope of this graph, and because this is the horizontal line, the slope is always 0, so the derivative is 0. This is an explanation of these results using the graph, but this is not a proof. To prove it, we have to use limits. We call that by definition of derivative dfx over dx is the limit of f of x plus h minus f of x over h as x tends to 0. And for this function, fx is equals to the constant function, is equals to k. So fx plus h is also equals to k. Because this is a constant function, no matter what the value of x is, the function value is always equals to k. So by definition, dk over dx is the limit of k minus k over h as x tends to 0. But k minus k is 0, so the limit is 0. This proves that dk over dx is equals to 0. This rule is not easy to prove. Note that we have the condition n is any real number. If n is an integer, then we can use the binomial theorem to prove this. By definition, we have dx to the power n over dx is equals to this limit. This is f of x, then this is f of x plus h. We can use the binomial theorem to expand the nth power of x plus h. It is x to the power n plus nc1, that is n, times x to the power n minus 1 h plus nc2 x to the power n minus 2 x squared plus all the terms up to the last term x to the power n, and then minus this x to the power n. Then we can cancel out x to the power n, and every term left is the multiple of h, so we can cancel the h with the denominator. So we have this limit, nc1 times x to the power n minus 1 plus nc2 times x to the power n minus 2 h plus and so on up to x to the power n minus 1. And as x tends to 0, all these terms will become 0. So the limit is equals to nc1 times x to the power n minus 1. That is n times x to the power n minus 1. So we have proved the rule, but only for n is a positive integer. So our next step is to show this rule when n is 0 and when n is a negative integer. If n is 0, x to the power n is x to the power 0, so it is 1. So dx to the power n over dx is d1 over dx. That is the derivative of a constant with respect to x, so it is equal to 0. And n times x to the power n minus 1 is also equal to 0 because n is 0. So we have this rule when n is equals to 0. When n is a negative integer, we still can prove this rule by using limits. But instead of this, we can use the quotient rule to prove it. This is the quotient rule. We can prove it by using limits. We have yet to prove it, but now we assume we have this rule. Then we use this rule to prove that when n is a negative integer, we have dx to the power n equals to n times x to the power n minus 1. If n is negative, we can let n equals to minus k. Then k is a positive integer, and x to the power n is equals to 1 over x to the power k. So dx to the power n over dx is equals to d1 over x to the power k over dx. Then we are ready to apply the quotient rule with fx equals to 1 and gx equals to x to the power k. So the quotient rule will give you these expressions: x to the power k times d1 over dx, that is equals to 0, minus 1 times dx to the power k over dx, over x to the power k all square. Now k is a positive integer, so dx to the power k over dx is just equals to k times x to the power k minus 1. So we have 0 minus k times x to the power k minus 1 over x to the power 2k. And this is equals to minus k times x to the power minus k minus 1. But minus k is equals to n. So this is equals to n times x minus k equals to n. So it is n times x to the power n minus 1. We have proved this rule for negative integers also. We have proved that this rule holds for all integer n, but we have to prove it for all real numbers. The next step is to prove that this rule holds when n is a rational number. But to prove that, we need the rule we call the chain rule. And chain rule will be included in the later parts of this chapter. So we skip it now. Next, we have these 4 rules. The proofs of these 4 rules are quite similar. I will not prove all of them. You can find it on your textbook. I'm going to prove the 4th rules, or in particular, I'm going to prove the addition rule when this is a positive sign. We have 2 functions here, fx and gx, but for this sum, we can take it as a function itself. So fx plus gx is itself a function, and by the definitions of derivative, it is equals to the limit. So we replace x by x plus h and put it here, minus the original function, and divided by h. As h tends to 0, this limit is equals to the derivative. And we can rewrite this one as the sum of 2 fractions, and you can write it as the sum of 2 limits. This is equals to dfx over dx plus dgx over dx. By definition, dfx gx over dx is equals to this limit. We can write it in this way. We have added 2 new terms, fx plus xgx, and it's negative. We can write this one as the sum of 2 limits. And because both terms here has the factor fx plus x, we can take it out and write it as the product of these 2 limits. And for the second fractions, we can take out gx. Because gx is independent on h, so we can treat it just like a constant and take it out here. But by definition, this is dgx over dx, and this is dfx over dx. And as x tends to 0, this one tends to f of x. So we have this right-hand side of the quotient rule. The proofs for rule number 3 and rule number 6 is just similar, and you can find them on your textbook.